Radio Solution, 로버트 바우맨이 항공우주 응용 분야에 대한 마이크로 전자 소자의 SEE 평가 요구사항에 대해 발표합니다. 로버트 바우맨은 미국 라이스 대학에서 박사 학위를 받은 뛰어난 물리학자이자 전기 엔지니어입니다. 29년간 TI에서 근무하는 동안 주요 신뢰성 위험을 식별 및 완화하고 방사선 영향 연구에서 획기적인 발전을 이끌었으며 ITAR 수출 통제법을 변경하는 데 핵심적인 역할을 하는 등 반도체 산업에 큰 기여를 했습니다. TI에서 은퇴한 이후에는 컨설팅 및 대학 연구를 수행하고 있습니다. 그는 수많은 프레젠테이션을 저술하고 2권의 책을 공동 집필했으며 17개의 특허를 보유하고 있습니다. 오늘 로버트의 첫 번째 발표는 특히 열악한 우주 환경에서 방사선이 마이크로일렉트로닉스의 신뢰성에 미치는 영향에 관한 것입니다. 그는 우주 방사선에 인해 위성의 80%가 유실된 최근의 SpaceX 별자리 발사에 대한 논의하는 것으로 시작합니다. 이 강연에서는 선량 및 단일 이벤트 효과의 주요 측면과 우주 방사선의 출처 및 변조에 대해 다룰 예정입니다. 강연은 샘플 준비 요건과 이온 선택 고려사항을 포함하여 SE에 대한 가속 테스트 중점을 두고 마무리됩니다. 로버트 박사님을 환영해 주세요.
Hello, everyone. This is Robert Baumann. I am basically going to give 2 talks today, both on single event effects, testing requirements. The first talk will be focused on basically the requirements for testing microelectronics for space use or space applications. And the second talk will be on terrestrial, so Earth-based applications. I am basically currently employed by Radiosity Solutions. It's basically a technical consulting company, and what I consult in is basically radiation effects. So without further ado, let me go to the next slide just to show what we're going to be talking about today. I always like to start discussions with kind of a motivation, so why you should listen to me. These are kind of long talks, so I want to make sure that we understand why it's important to consider single event effects and their reliability impact. Then I will do, since some of you may not have so much experience with heavy ions, I'm going to talk a little bit about linear energy transfer and range in heavy ion and particle physics. This is our metric for how strong the ion is. And as we'll see, different strength ions produce different single event effects. Then at a very high level, we'll talk about both dose and single event effects, just so you understand, if you hear it or you see it in a paper, the difference between dose and single event effects. Of course, most of this talk is concentrating on single event effects, or the acronym SEE. We're then going to focus on kind of a quick summary of the space environment. In other words, what types of radiation do we find in orbital, especially orbital environments? Then we'll look at accelerated test needs for space, ion test challenges. So like any radiation test, there are some physical challenges to having the test be done correctly and get good results. So we'll talk a little bit about that. And then as an example, I will just show how we generate a single event effects cross-section and determine an event rate in orbit. Since that's our primary concern, we have these heavy ions that are producing nuclear events in the integrated circuits. Those events produce single event effects, which can be both destructive and non-destructive. So the rate of occurrence is very important, and that's kind of the key component of testing. We want to get at the rate, and then I'll summarize. Okay, so as my motivation for this talk, I picked one of the more recent and maybe famous space failures. This was SpaceX was launching a constellation of 49 satellites. And the concept of the constellation, of course, is to have many satellites create a grid, a communication grid. They're all in orbit moving together. They talk to each other and they talk to the Earth. So you can have kind of a continuous coverage. And you have some resiliency because you have so many satellites. So these are smaller satellites, again, in a constellation, meaning a very large grid of satellites. Hundreds or thousands of satellites are in orbit at any one time. SpaceX has been, they've done things their own way. So they've used a lot of consumer off-the-shelf components or COTS components. They've stayed away from radiation hard components in general. And so this was the result, I believe, of some system component or microelectronic circuit in their satellites that had a very high failure rate that was undetected until they put it in orbit. Effectively, they lost 40 out of 49 satellites. Now you have to be a little careful. All I got was from the news. I didn't actually get any data. So from their news clippings, they claimed that geomagnetic storms, we'll talk about that in a few slides, made the atmosphere denser. And then basically their Starlink satellites couldn't raise altitude. They lost altitude and finally burned up in the atmosphere. The thing that's a little bit concerning about this is typically satellites have automatic programs that are either sleeping during launch or can turn on after launch, but something didn't turn on in the satellite. So I think there's more to the story than just the atmosphere was thicker than they expected, because they should have predicted this. So again, I don't know for sure, and I'm not saying I don't have access to the SpaceX data, but from this discussion and the large failure rate, it looks like it might be a subcomponent, an electronic system that failed, maybe in the power supply. So these couldn't power up and they couldn't adjust their altitude and hence they failed. So it leaves a question, did radiation-induced destructive single event effects cause a failure to awaken? And again, the failure rate was very high. And I'm sure from a business standpoint, SpaceX has insurance. And again, because the constellation, the plan for the constellation is basically to have thousands or at least many hundreds of satellites. I think they can afford a failure rate that's relatively high. And that's a big difference between traditional space, where you put people into space, and a lot of these satellite programs. The acceptable failure rate can be a lot higher. So as reliability engineers, this gives us more flexibility in terms of managing the risk and reliability performance window from conventional space applications. All right, so that was motivation for the talk. Now I want to talk a little bit about linear energy transfer, or LET, and range of ions. So as the picture on the left shows, for basically particle radiations, so here I just show a red circle. It has some kinetic energy, some initial kinetic energy. As the particle travels through matter, okay, whether it be silicon or any other material, it's going to lose energy through interactions, both scattering interactions with nuclei as well as generally interactions with the electrons. So as it travels, it's losing energy. And so linear energy transfer is a measure of that energy loss along the path. So you see E1 is greater than E2. And over this small path, we can define an energy loss. So the LET, the definition of LET is dE dx. Now, this is kind of an engineering calculation. It's very useful. Any physicists in the audience may be rolling their eyes a little bit because there's a lot more involved. There's a lot more energy loss mechanisms. And LET is really focused on energy loss mechanisms that create ionization. And of course, from a microelectronics point of view, that's what we care about, because it's these bursts of ionization or charge creation that cause single event effects. So I show here in the equation LET equals dE dx. So we're measuring or effectively calculating how much energy is lost over this small path traveled. Okay, and I put electronic here as a subscript just to make sure that people understand there's also a nuclear component. And we don't generally worry about that unless we're talking about other kinds of effects. And I'll talk about that a little bit later. But LET is a measure of how much disturbance an ion creates. So typically, heavier ions that are more positively charged with higher energy will deposit or lose more energy faster than a lighter ion, like a proton or a helium alpha particle versus a carbon atom or an iron atom. The iron or the carbon will have a much higher LET. So the energy density deposited in the silicon will be much greater. So typically when we're worried about destructive events, the heavier the ion, the more destructive. On the right-hand side, I show a plot showing the two different things I'm trying to measure. And by the way, LET is also referred to as stopping power. They're not exactly one-to-one, but to first order, you can call it stopping power. Most people say LET. So the yellow curve is my LET curve. And basically this is for iron. So I've taken an iron ion and I say, okay, as a function of energy, this is what the linear energy transfer or energy loss over the path is for this ion. And you'll notice several things. First, at very high energy, the particle is moving very quickly and doesn't have time to interact with the electron so much. So it's not losing as much energy. As it slows down more gradually, it has more time for Coulombic interaction forces to respond. And so now as it slows down, it loses more energy. So actually, if you consider a particle, let's say it started with 400 MeV. Okay, so we come up here and we're just following. The LET is actually rising. Okay, so the efficiency or the amount of charge generated is actually increasing as the particle energy is decreasing. And again, that's because particle energy going down means the particle is slowing down. So it has more time in the circuit, it creates more charge. Now, the Bragg peak will be important later, and I'll talk about this when we talk about actual testing and some of the issues. Bragg peak is just the maximum. Okay, that's where it's losing the maximum amount of energy. You'll notice once we go beyond the Bragg peak, so we start losing more energy beyond, it drops very quickly because effectively now the particle is moving so slow, it just doesn't lose much energy and it almost has no energy left. So beyond the Bragg peak, it's very steep. And in general, when we're testing with heavy ions, we don't want to operate in this area. And the main reason is ideally for a good heavy ion experiment, you want LET to be constant in your device volume. So typically, let's say a device depth is 1 micron to 10 microns. We want the LET to be as constant as possible. So we want to be to the right, okay, where it's relatively flat. If you're on the left of the curve here at the low energy, you may have an LET range from, in this case, 30 down to 10 in a very small amount. So it's very hard to understand the acceleration factor. So in general, we make sure our experiments are to the right of the curve in the higher energy. And then range is kind of obvious or self-evident. Obviously, a more energetic particle is going to be able to go further, okay? So that's what the range curve shows you. It starts at high energy and goes down, and as we reduce the energy of the particle, it just doesn't go as far. And the range is important because anytime we do an experiment with heavy ions, we want to make sure that the particle that we pick, the ion that we pick, has enough energy to traverse. If we're doing it in air, for example, it has to go through several centimeters of air maybe in the experiment. Then we typically have an open package, and then it has to go through the different layers of the semiconductor before it gets to the active layers in the silicon. So we have to make sure that we have enough range, that the particle has enough energy. And then again, we want to be far away from the Bragg peak. In other words, much higher energies than the Bragg peak. And I'll get back to this. I know that's a lot of talking. Even though this talk is focused on single event effects, in space, you really have two major effects, the single event effects and dose effects. And there's actually two types of dose effects. So the kind of one of the dose effects we hear about a lot is total ionizing dose. This is the effect of charge trapping in insulators. So imagine you have a semiconductor chip that's in orbit in your satellite. It's going around the Earth, and it's being exposed to very high levels of radiation. Now, yes, some of that radiation is going to cause single event effects, and these are very different than dose effects. But dose is like a sunburn. So I'm showing this person down here with the red face. It's very much like humans in the sun. Okay, it's not one photon, but it's many photons that give us a sunburn or a suntan. Total ionizing dose is like that. It's kind of a monotonic progression. As you expose the device longer and longer time to a fixed radiation source, actually the device parameters start to shift in time. So kind of like an aging. So if you're familiar with hot carrier or NBTI, that sort of transistor aging, total ionizing dose and total non-ionizing dose are very similar in terms of basically making products shift. So parameters shift. It's usually not an instant failure. Okay, and that's why we call it a dose effect. So you have to be there for a certain amount of time in orbit before you see it. Now, just to clarify the difference between the two dose effects, basically total ionizing dose is the creation of charge in a dielectric, okay, in insulating layers. And because of the differences in mobility between holes and electrons, so the radiation goes through our device. Anytime the radiation passes through a dielectric, if it produces an electron-hole pair, the electron gets moved out of the dielectric very quickly because electrons have relatively high mobility, even in insulators. However, holes do not. So you start accumulating holes, basically positive charge in your dielectrics. And if you have any electric fields in your devices, which you usually do when the device is on, those holes will be moved in response to that electric field. And unfortunately, for both MOSFETs and bipolars, where that charge moves is usually in a bad place, and it affects the transistors. In MOSFETs, you get threshold voltage shifts and leakages. In bipolar transistors, you get basically minority carrier lifetime reduction, which from a design point of view reduces your beta. So the amplification of your transistors goes down as dose increases. Now, total non-ionizing dose is often also called proton dose or defect density. So PD or DD, those are much easier to say. This is the concept that when you throw radiation at a nice crystal structure like silicon, some of the interactions are actually going to liberate silicon. So you're going to get a vacancy and an interstitial produced. Okay, so those are defects. And many of these defects are electrically active. And so again, overdose, you get more and more defects accumulating, and this changes the electrical properties of your transistors. Now, MOSFETs tend to not, because they're majority carrier devices, they tend to be less sensitive to this effect. However, bipolars can be very sensitive to this effect. In the bipolar, basically the base region, so carrier lifetime is really important to give you a good gain. Any defects in the base are going to tend, and these defects are going to reduce the carrier lifetime. And so effectively, your amplification capability or your beta goes down over dose, both from total ionizing dose and this defect density dose. All right, so that was dose. I'm not going to talk about dose again. It is an important problem with space, and we do have to test for it. But again, the topic here is single event effects, so that's what I'm going to focus on. And like the name implies, single event effects are basically like a lightning strike, like what I'm showing on the right. It's a one-time event. So one radiation event occurs, whether it's a heavy ion or a neutron or a proton, and then you get some excitation in the silicon and then some circuit response. And sometimes the circuit response is nothing. The circuit doesn't care. Other times it cares, and you get maybe a soft error, a bit flip. And other times, if it's in a power circuit, you can actually burn out the circuit. So there's a whole range of different single event effects, and the single event effect that you see will depend on the circuit design, the technology, as well as the incoming radiation. So again, if we have a very heavy, high LET event, like a heavy ion, we can get destructive events, or say very large multiple bit upsets in your memories that are not correctable. If they're much lighter or much lower LET, then we get single bit failures. We don't usually get, destructive events. All right, so that was a very quick review of kind of the key radiation effects, the 3 key radiation effects. So now I'm just going to very quickly review single event effects. So every single event effect is basically a single event transient. If you just think of bulk silicon, or maybe a junction in silicon, Effectively, the ion passes through the silicon. It generates a lot of electron hole pairs. And what happens with those electron hole pairs and what they do to the circuit depends on the circuit design, critical charge, and all sorts of other parameters. So effectively, if you consider just a block of silicon and a radiation event, you get some single event transient. And it's transient because just like nature doesn't like a vacuum, electronics don't like free charge, like an excess charge. So either recombination is going to make the charge go away, or if you have electric fields, you're going to move the charge away. So transport and recombination tend to make radiation-induced charge go away. Now, again, depending on the response of the circuit, how much resistance it has to that charge transient, you get different effects. So SBU is single bit upset. MBU, I already mentioned, this is where one event creates multiple bits to upset. This is a big problem in memories. If you're correcting with error correction, typically you can correct a single failure, maybe detect two. Sometimes you can do more. But if you get an event that's 10 bits wide in a single correction word, this could be uncorrectable. And single event functional interrupt, that's kind of a catchphrase for many different problems that can happen in complex digital circuits, particularly with flip-flops. If you're using flip-flops to store state variables of a machine, and these get flipped at the wrong time or in the wrong place, the entire system can misbehave. So Cepheid is kind of a force multiplier in the sense that one single event in, for example, one flip-flop may actually turn a DRAM that's reading data now writing data, for example. So it may actually transform the operation. And of course, any bits that are written to that were not supposed to be written to are going to be errors. So you can see, maybe thousands or millions of errors when a Cepheid occurs. It can also be kind of for example, a microprocessor that gets into a stuck state and no longer is working. That would also be an example of a Cepheid. These are all considered single event upsets, okay? And they're all considered non-destructive errors because effectively, if you write new data to your memory, you can get rid of the errors. If you reboot your processor, you can start the process as if nothing happened. They're non-destructive events. Okay, the ones that are in red at the bottom are basically potentially destructive. Single event latchup is one of those that's it can be destructive, and I would say it's usually is destructive, although you may not detect the destruction. In other words, a single event latchup is just like an electrical latchup. The only difference is that it was a radiation event that created the latch. Because it's a high current state, and because typical electromigration design rules maybe have a 2x or 4x redundancy factor, single event latchup can generate a lot more current than that. So you may actually have damage from electromigration when a latchup happens. And in fact, many people who use commercial circuits in space will make a current detector on their power supply. And if they see a very large increase in current, they shut down, for example, a microprocessor. They'll just power down the microprocessor. And so if you do this quickly enough before the currents have really gone too high and metallizations have become too hot, you can perhaps extend the life of the microprocessor by doing this. Now, the last two, single event gate rupture and single event burnout, I don't have time to talk about in detail, but for power electronics, these are incredibly important. And these are typically produced by heavy ions, okay, high LET events. And they're kind of the fundamental limit or reliability limit for a lot of power products in space is determined by these two mechanisms. And generally, people will specify that our part is good up to an LET, an ion LET of 60, and showed no single event gate rupture or single event burnout. Meaning if you take it above 60, you may see some burnout. And this then leads to a event rate. And the customer has to decide, can I tolerate or should I use a different part? Okay, so that was very quickly review of the acronyms. Now I want to spend a little bit of time on the space radiation. Okay, so this is one slide for a very complicated topic, but hopefully you'll come away with some feeling about the space radiation environment, even though it's somewhat simplistic. So there's effectively two major sources of radiation in space. One are the so-called galactic cosmic rays. And if you've worried about neutrons on the Earth, you've probably already heard about them. They do produce neutrons on Earth, but they also produce a lot of protons in orbital and planet environments. So we do have to worry about these. These are very, very high energy protons, along with some heavy ions, okay? Now, the other source, of course, is our sun. This is giving off, of course, we see light, so photons, a lot of electrons, a lot of protons, some heavier ions as well, although at lower energies as compared to galactic cosmic rays. So galactic cosmic rays have been accelerated for billions of years across galactic distances. So those particles are highly relativistic, okay? They're going very close to the speed of light. So you have, and I should mention it's an energy distribution, but incredibly high energy protons generally with a few heavy ions. The sun is less energetic, but still can produce some issues. Now, the thing that makes especially orbital calculations interesting is the Earth has a relatively strong magnetic field. And so you can think of the Earth's magnetic field as a transfer function. So it takes all this incoming radiation from our sun, from the galactic sources, and because magnetic fields will bend charged particles, make them on curved trajectories, we basically get accumulations of charge. This is the so-called very famous Van Allen belts. And this diagram in the middle is a cross-section. So these belts are actually like a donut around the Earth. And generally, people that fly spacecraft want to stay out of the belts because the radiation, both dose effects and single event effects, are many times more intense if you live in these belts. So very often, you've heard of low Earth orbit. These are all very close to the Earth. A lot of them are around the equator. Some are polar, but they'll avoid these Van Allen belts here. And then you may have heard of geosynchronous orbit. This used to be a very famous orbit for communication satellites, and it's much farther out than the Earth's magnetic field generally reaches. So you get no accumulation so you're outside these belts effectively. But the key point here is this is a modulator of the space radiation. So if you're calculating reliability models for satellites, you have to know exactly the orbit. And the key orbit, obviously, is apogee and perigee, or altitude. Okay, so how far are we from the Earth? Inclination is very important. So that's really like latitude. So again, as you can imagine, basically being in around the equator, equatorial latitude, you get a lot of shielding because these Van Allen belts, even though they're high radiation accumulation, they're actually electrostatically shielding your device. So typically, if we run failure rate calculations for a equatorial orbit, it's very good. It's actually a relatively safe place to be. Whereas if you're on a polar orbit where the magnetic fields are normal to the Earth's surface, you get almost no shielding. So you'll actually see much higher failure rates there. That's just an example of how important the orbital environment is. So you have the two sources, galactic cosmic rays and the basically solar emissions. Those are modulated by the Earth's magnetic field, and that's a function of what your orbit is. And finally, you get this curve that I show on the right. This is basically showing a low Earth orbit. It's the integrated flux. So we're integrating from high energy to low energy. And we're just showing, and this is particles per centimeter squared per day. And as one would expect, as you go to lower and lower LET particles, again, the horizontal axis is LET, linear energy transfer. So low LET means maybe you can have a few SEU or SEE, kind of low energy. Once you get to the higher LET, like 20 or 30 or above, you can start having destructive effects. And that's why people care about testing with heavy ions. And so this just shows you a typical example of the LET environment. Okay. So I'm switching gears now. We talked about the different radiation effects. We also talked about the environment. And so now I want to focus on, okay, so somebody has hired you, or you're working for a space company and you want to know, okay, what are the things I have to do a heavy ion test? And again, heavy ion testing is typically just for single event effects. If we wanted to do dose testing, displacement damage testing, those are different types of tests. And again, I don't have time to talk about these today, but okay, I have an animation here. So one of the key requirements of heavy ions is because they have such high LET. So again, high LET means they lose energy very quickly over distance. They don't go very far. In fact, many heavy ions very energetic heavy ions will only go a few microns through solid material, or tens or hundreds of microns through solid material. So what that means is if we're testing a part that we've purchased, we have to deprocess it. So here I show mold compound. Typically this is mechanical grinding and then some chemical etching to reveal the die. And so you want to see the die surface, and hopefully then your heavy ion beam can actually activate or instigate single event effects in the silicon. If you're making your own die, or you have access to die in ceramic, that's actually much easier to deprocess. You can basically just heat the solder. Sometimes you don't even need to heat the solder. You can use a sharp knife and actually pop the top off, so you have direct access to the device. But that's kind of a key requirement of most heavy ion facilities. Now, there are a few heavy ion facilities that have much higher energies, like 10 times higher than the typical cyclotron. In the US, there's 2. In Europe, there's at least 1, and I think there's 1 in Germany coming online pretty soon. And these may be able to provide heavy ion testing without any depackaging. And if you've ever depackaged, you know that that's a pretty good that's a good feature to have if you don't have to waste time on depackaging. One of the problems with depackaging, of course, is you have to buy multiple units. Typically, you'll break a few when you depackage. If you're really good or have some really good technicians, you're lucky, then maybe every package is 100% yield. But in general, it's difficult. It costs some money, and it costs some time to prepare samples. Okay, so this is basically a snapshot of what Texas A&M has a cyclotron. This is very close. I live in Dallas, Texas. And so basically it's about a 3-hour drive for me. So it's very easy for me to access. Now, as with all heavy ion facilities, the demand is so high. I'm lucky if I get maybe 4 or 5 beam opportunities per year. And that's because I'm working with a university. As a commercial customer, you really have to fight for beam time. So this is one challenge moving forward that's completely outside of the test requirement discussion. It's just test availability, or beam availability is really a big challenge moving forward. So anyway, this plot on the left shows basically, it's another way to kind of show the Bragg curves. We're showing linear energy transfer, or LET, on the vertical axis, and then we're showing the range. So remember I said it's very important to understand the range and the LET so that you can pick the right ion for your particular test. And part of the testing is also you want to pick a linear energy transfer that is of interest to your customer. And that will be determined on the orbit they're running in, what an acceptable failure rate is for them. And that's pretty complex, and I won't spend too much time talking about that. But let's assume you have an LET that you want to hit. How do you pick a heavy ion for your experiments? So just a few things about this curve. Now, Texas A&M does all their testing in air. Brookhaven and some other cyclotrons do testing in vacuum. I like air because you don't have to do any special thermal, heat transfer stuff. In vacuum, sometimes if you're running a hot circuit, the temperature can run away from you. It's just a lot easier. The price you pay is that you're losing energy in air. So I don't know if you can see these dots on your screen, but the triangles are immediately after the window, and then the little diamonds are after 3 centimeters of air. So you lose energy, and remember I said initially as you lose energy, your LET goes up. So let's say we were targeting an LAT of 60. So this PR 141 would be ideal. But you see, if we're too far away, then the LAT continues to increase. So maybe we would pick xenon, and most heavy ion facilities have degraders. These are thin metal films that you can put in the beam to reduce the energy. And by reducing the particle energy, we can move up this curve. So by using a degrader, you can basically get anywhere along this curve that you want for a particular ion. Okay, so again, if our goal was 60, I would probably take xenon and degrade it to 60. So in other words, put a couple films in the beam. It doesn't stop the beam. All it does is reduce the energy, which increases the LAT. So xenon coming out of the beam is something like 52. We put a degrader in and we get to 60. So that would be an example of tuning. Okay, and then we look down on the chart and we see, oh, 90 microns. So as long as our silicon device, and that includes everything, the passivation oxide, the different metallizations, dielectrics between the metallizations, down to the silicon. As long as that's, say, 40 microns or something, then I know I have 50 microns of range left. Now, in some power devices that have very deep implants or use the entire substrate, then you're probably going to want something with much larger range in hundreds of microns to give you an accurate single event effect. And I'll talk about that in just a moment. Okay, which ion beam should we use? That's the million-dollar question. What I show on the right is a plot, again, of my low Earth orbit, again, the integral flux, and I'm showing several different conditions. And so depending on the customer's condition, let's assume the customer says, you know what, if we get 10 to the minus 4 events per centimeter per day, that's good enough for our reliability, for reliable operation in orbit. Okay, so that means if I'm in this orbit, this first green line, basically, as long as the part can survive, say, an LET of 10 with no failures, then it will be reliable in the orbit. Now, this different orbit over here, I would have to test out to 20. So LET 20 would be kind of the magic number. If I'm on this other orbit here, 30 would be the magic number. And in fact, for most, longer term space missions, typically people will test to 50 or 60. And if they see no failures or a very low failure rate, if it's non-destructive and it's a low failure rate, that's okay. If it's destructive, generally you want 0 failures. So they will test to something like 50 or 60. And of course, for radiation hardened, which ends up for the US at least is export controlled, if you test anything above 80 and it survives, that's considered radiation hard. But I would say for many, many space applications, something from 50 to 70 is already a fairly hard microelectronic circuit. And there are consumer circuits that can survive that kind of heavy ion LET. So the red region here is showing you, the red curve I should have mentioned, this is for flares. So the solar activity is made up of a lot of different components. It also has its own dynamics. So you get solar storms. If these storms produce, for example, they're called coronal mass ejections, you get a snap of the solar magnetic field, and it's like a cannon. It sends a whole bunch of protons and heavier ions in one direction, like a gun. Okay, now if the Earth and your satellite is in line with that number of solar particles, you're going to see a very large increase in radiation. So you can think of these, the green curves that I show are different orbits under kind of the average environment. The red curve is kind of the extreme environment when there's a solar storm. Like the one of the SpaceX that I mentioned, that was a solar storm. Okay, and that causes all sorts of problems in the atmosphere. It ionizes the atmosphere. We see the aurora borealis, that's actually ionization in the atmosphere. And of course, any satellites are going to be suffer much higher exposures to radiation. So when you're trying to determine where to test, you also have to consider solar flare activity or these solar storm activities. And I show the region here because the red curve is based on the worst week. I like to use that as kind of the upper, it's the worst measured week in terms of total solar radiation. So I think it was in 1989 or something in the 80s, basically. And most storms are less than that. But as a conservative reliability measure, worst week is a very good thing to use. Now, luckily for us, solar flare activity typically lasts a couple days, maybe a week or two, and then it dies down. It may still be higher than the average, but then it's within 2x, 5x, something of these green lines. But the key point is you do get a region, and you have to work closely with your customer to determine, how much risk are they willing to assume. If the answer is we want zero risk, we don't want to have any failures, then you're probably going to have to buy rad hard electronics that can survive 70 to 80. If you're willing to assume some risk and say, okay, we have 1,000 satellites and we're willing to lose 50 of them, okay, maybe we can test at 40 or 50 heavy ions with LET of 40 or 50, and if they pass that, then that's okay. All right, so again, this is too short a talk to talk about all the intricacies or details of how to figure this out, but I just wanted to give you a sense that every customer has different needs because they have a different orbit and they're going to have different electronics, and so you have to kind of customize the program for the specific customer. All right, earlier I talked about the Bragg peak. This is kind of my cartoon. Again, it's just showing the energy. So we have the plot here, ion energy, and LET is here. And so as I said, at very high energy, all it is that curve I showed earlier on a side. But I'm trying to show also the range. So if we pick a lower energy ion that can only get through the plastic package, or maybe this is the oxides above the device, this would be an example where I've picked an ion that does not have the range to reach my device. So in this case, I showed the plastic, but of course, for most heavy ion tests, we would have the plastic removed. But you could still pick a very low energy or high LET ion that doesn't have enough range to get to your sensitive area. And I should mention the red region here is the area we want to hit. This would be an example that, yes, we're in the red region, that's good, but we're so close to the Bragg peak, we have very high uncertainty of what the LET is. So you can have a model, but of course it's statistics. So you could have LETs from the peak all the way to zero, and they're all in your device. So if you see an upset, you don't really know what the sensitivity to LET is. This is kind of the ideal cartoon here, and it's showing you the very small change in LET in the actual device volume. This is the ideal kind of cross-section that you would like to see in typical testing. And I show an example here. This is a very good paper from a NASA guy. He's talking about failures in power MOSFETs, and the manufacturer's data was based on these three heavy ions here in the green shaded region. And you note these curves are showing you the range, okay? And so the problem was that this power transistor had active layers that went from the surface all the way to 40 microns deep in the epi. And unfortunately, the heavy ions that the manufacturer used that made the data sheet was in the green. And you can see a lot of the LET is just dropping off here. So what that means is in space, you have heavy ions that are going to go completely through your device and generate much more charge. And so those ions, even though their LET is lower, they have longer range, they're actually worse. So if you look at the plot on the top, this was the predicted manufacturer's data. What this is telling you on the vertical axis, they're telling you, here's the gate voltage you can operate at, okay, or drain voltage. And on the horizontal axis is the LET. They're saying, oh yeah, if you're in an environment and you want to survive up to 40 LET, you have to drop, I think this was a 1,000 volt device. You have to drop to 800 volts or lower. The red data is actually the NASA data, and it's telling you, no. You have, maybe at 800 volts, maybe you could operate up to 30, but you're not going to get to 40. By the time you get to 40, you're already failing at 400 volts. So again, I don't have time to discuss the whole process of breakdown in the power transistor, but effectively, if you increase the drain voltage on a power MOSFET, you increase the probability of a breakdown event, okay? So what this is saying is, how much do I have to reduce my drain voltage so that I don't fail in space? And the result depends on the heavy ion that's used. So again, this is a very clear example where the manufacturer and NASA disagree strongly. And unfortunately, NASA is correct. And they're saying this transistor is not as good as what the manufacturer is saying. So if you used it in space and believe this green curve, you will have failures, okay? I'm running out of time here, so I won't spend too much time on this. This is an application that I wrote while I was still at Texas Instruments. Very simple program. It just takes SRAM code. This is basically calculating energy loss in layers. So you can build up your stack. This is your device stack, so back end of line, all the metal barriers. And it takes an ion and calculates how much energy is lost through the layers. So it tells you how much range you have, and more importantly, it tells you what is your LET in the key region that you care about. And we use this all the time at TI, and it helps you stay away from this problem of getting the wrong LET and the wrong conclusion. Okay, so how do we calculate a device cross-section? This is very simple, and I won't spend too much time on it. Effectively, we turn the beam on, and then we look for failures. And so whatever that failure is, if it's bit flips, or if it's burnouts, or if it's latch-up events, we count the number of events, and we divide by the flux, or the entire fluence of the test. Okay, so it's number of upsets divided by the fluence. If they're destructive events, usually it's only the number of events is 1. So we consider fluence to failure in that case. And that gives us a device cross-section in centimeters squared. So if you think about physically, what it's telling you, here I have just a cartoon of the chip. The red areas are my sensitive areas. So those sensitive areas are going to be some subset of the total chip area. There's some parts of the chip that are not going to be sensitive. Okay, so symptoms of latch-up are generally, I mentioned already, you get very large increases in current spikes. I'm just giving you examples of some things that you want to look at when you're testing your devices. And then in single event gate rupture, this is where the oxide dielectric is actually breaking down. You'll typically see increases in gate leakage. And then all of a sudden you'll see these large steps, okay, in both gate and drain leakage. And eventually the steps add up. And it's very much like dielectric breakdown under electric field stress. You get some soft breakdown, and eventually you get hard breakdown. Now, the hard breakdown happens much faster if you're at higher voltage, or if the ions have a higher LET. So again, that higher LET is very important for destructive events. Just like a lot of reliability people, we use the Weibull function. In this case, we use the Weibull function to get the cross-section curve. And just the key aspects of this cross-section curve are the threshold or onset LET. So if you have a roughly robust device, maybe you'll see no events, no failures up to a certain LET. Once you get to a specific LET, this curve kind of turns on. And then you get into a saturation region where the curve is flat, okay? And wherever the curve is flat, that's called the saturation cross-section. And we can use this to calculate an event rate. And I'll show that in the next slide. So basically, we use the differential flux. So I showed the integral flux before, but since we're doing an integration, we use the differential flux. So the red line is our orbital flux calculated for a specific orbit. The blue curve shows our single event effects cross-section that we calculated from measurements, heavy ion measurements. And effectively, we're taking the area under these two curves, and that gives us an event rate. So in this case, 4 × 10⁻⁶ SELs a day. And so the equation here for event rate is up here. It's a typical reliability calculation. So the hard part is doing the heavy ion test and basically getting an accurate test result. And then just doing this integration is actually fairly easy. And once you have an event rate, you can discuss with your customer, is that, for example, for latch up, is that an acceptable event rate? And if they have a 6-month mission, they may say, oh yeah, that's fine. If they have a 10-year mission, of course, the same failure rate may be unacceptable. So that's where you have to talk with your customer and optimize. All right, so in summary, I went a little bit over here, so I apologize. Space radiation is dominated by protons, both from galactic and the sun. You have a few heavier ions, And as I said, that's a small fraction, but because the heavier ions are more damaging, we really have to worry about them. And so basically, when we do testing for space, at least for single event effects, we're generally going to a heavy ion facility. And for sure, as well, we're going to proton accelerators. Again, because there's so many protons in space, we get a lot of information by testing with protons. Prior to single event effects characterization, it's crucial to understand the orbit. And I showed some examples of how different the orbits look, depending on where they are, when they are, altitude, and that sort of thing. And that influences all the decisions about what LET you should test at. Now, due to the limited ion range, especially with the higher LETs, you basically have to deprocess your dye. There are a few exceptions to this, very high energy facilities, but in general, you have to consider that you're going to have to prepare your dye for testing. So unlike neutron testing that we're going to talk about next, where you can just put fully packaged devices and in fact, put many packaged devices in a beam in parallel, with heavy ions, it's one device at a time and they have to be deprocessed. And as I was finishing up, ion energy and LET must be picked carefully to ensure that the entire sensitive volume is irradiated. This is especially true of deep devices, for example, vertical power structures and things. You want to mimic the space conditions. And if you pick the wrong LET or too short a range, you will overestimate how robust your device is. In other words, you'll underestimate the failure rate. And just as some rules, at the last statement here for basically destructive single event effects, so this is latch up and burnout. Basically, we generally test with heavy ions to 10 to the 7th particles per centimeter squared. So the fluence is 10 to the 7th. If we see no events, that's considered a pretty robust product if it's at the target LET. For non-destructive single event effects, these are ones that are recoverable. Of course, we can accept a higher failure rate. So typically it's 10 times lower. We test to 10 to the 6th ions per centimeter squared, unless in some cases, the single event effect rate is so high, all we need is to test to maybe 1,000 errors or something like that that gives us good statistics. And that may be much less than 10 to the 6th. So we just define it by the part. So that's pretty much it for this. And unfortunately, I won't be able to join you when this actually airs, but I am open to questions. If you want to send me questions via email, that's fine. All right. Thank you. Bye-bye.